Hello everyone, welcome back to our channel. This is Dr. Prafulla Dikshit, and today we are diving into a fascinating topic that combines strategy, decision making and real world applications. Yes, you guessed it, we are talking about game theory in operations research. But wait, what exactly is game theory? Well, imagine a world where players, whether they are companies, governments or even animals, make strategic moves anticipating each other's actions. It's like a high-stakes chess match where every decision matters. In our presentation, we'll explore the key principles of game theory and how they apply to operations research. Think of it as a toolkit for optimizing resource allocation, supply chains, and pricing strategies. Ever wondered how companies coordinate their supply chains? Game theory has the answers. We'll unravel the mysteries behind supply chain decisions, inventory management, and order fulfillment. And pricing strategies? Oh, we've got you covered. Whether it's setting the right price for your product or navigating the competitive markets, game theory provides those aha moments. Plus, we'll peek into the world of auctions, bidding wars, sealed envelopes, and optimal strategies. Trust me, it's more exciting than it sounds. But here's the twist. Game theory isn't just about winning, it's about understanding the delicate balance between cooperation and competition. Sometimes, the best move isn't what you'd expect. So, whether you are a business enthusiast, an inspiring economist, or just someone who loves unraveling puzzles, this presentation is for you. So hit that subscribe button, ring the notification bell, and let's embark on this intellectual journey together. Don't forget to leave your thoughts in the comments. I'll be reading them. Thanks for tuning in, and remember, life's a game, so play it wisely. Now, without further ado, let's get started with the lesson. So, as per Peter Bernstein, game theory says that the true source of uncertainty lies in the intention of others. So what is this game theory all about? It's a set of tools and techniques that help us make decisions under uncertainty. When there are two or more intelligent opponents, but how does it assume a place of importance in the several different fields? So let me tell you, it's a fascinating field. It's a captivating area of study that explores strategic decision making. It's like a mental chess match where players, whether individuals, companies or nations, strategically interact. It provides optimal solutions. Imagine playing a game where your goal is to win or maximize profit or at least minimize your losses. Game theory provides tools to find the best strategies for achieving these objectives. At its core, game theory is a mathematical framework. It uses models, equations, and concepts to analyze interactions among decision makers, that is, the players. These decision makers could be competitors in a market, politicians in an election, or even animals in an ecosystem. Thus, game theory helps us understand how rational actors make choices in competitive situations, aiming to maximize their gains or minimize their losses. It's a powerful tool with applications across various fields. It has intriguing applications in various fields like economics, biology, political science, and operations research, and many more. Now let's see how this mathematical framework impacts our world. In the field of economics, game theory is a powerful tool. Here's how. Game theory helps us analyze how firms, consumers, and competitors interact strategically, whether it's pricing decisions, product differentiation, or market entry. Understanding these dynamics is crucial. In terms of pricing strategies, companies adjust prices based on competitors' actions, and game theory guides firms in setting optimal prices while considering rivals' reactions. What about auction design? From spectrum auctions for telecom licenses to online platforms like eBay, game theory ensures efficient auction designs. Impact of dominant firms. When dominant firms make decisions, for example, mergers, pricing changes, game theory predicts their impact on the overall market. Even biology is not free from the influence of game theory. So nature is full of strategic interactions, and game theory helps us decode them. In terms of behavior evolution of organisms, have you ever wondered why do animals cooperate, compete, or exhibit altruistic behavior? Game theory sheds light on these evolutionary puzzles. In terms of interactions between organisms, whether it's mating, cooperation, or aggression, game theory explains animal behavior. You can think of it as a survival of the smartest. Well, even diseases play by the rules of game theory. How do pathogens spread? How do hosts respond? Game theory models help us understand and combat diseases. In the field of political science, you might consider politics as a strategic game, and game theory provides insights. For example, in international relations, different nations engage in strategic interactions, diplomacy, arms race, and negotiations. So game theory predicts outcomes and guides foreign policy decisions. In legislative bargaining in multi-party systems, lawmakers negotiate and form coalitions. Game theory models help us understand these intricate processes. In electoral competition, so have you wondered why candidates choose specific campaign strategies? Game theory explains how they position themselves to maximize votes. But wait, game theory isn't limited to academia or grand political scenarios. It's applicable in everyday choices, whether it's choosing a route during rush hour or deciding whether to invest. We are all players in the game of life. Strategic thinking. Game theory encourages us to think strategically, weighing risks, anticipating others' moves, and maximizing our outcomes. Well, come to think of operations research. And finally, operations research is a major application area. In terms of resource allocation, game theory optimizes allocation of resources, whether it's product capacity, R&D funds, or supply chain coordination. In terms of supply chain decisions, coordinating suppliers, manufacturers, and distributors, game theory guides these complex decisions. Consider pricing and auctions. Optimal pricing, bidding strategies, and auction designs all fall under the game theory umbrella. So remember, game theory isn't just a theoretical concept. It's everywhere, shaping our decisions and interactions. Operations research is one of the major application areas as it combines decisions and interactions from various different fields and makes use of game theory principles to solve business operations problems. So, game theory has a rich history. It's been developed over several years by brilliant minds. Notably, three economists, John F. Nash Jr., John C. Harsanyi, and Reinhard Selten were jointly awarded the Nobel Prize in 1994 for their groundbreaking work in game theory. Their contributions laid the foundation for understanding strategic interactions and decision making. So, at its core, game theory is designed for decision making in competitive or conflicting situations. Imagine players, whether they're chess grandmasters, poker players, or business executives, strategically maneuvering to achieve their objectives. Game theory provides tools to analyze these interactions mathematically. So, in a game, each player aims to maximize their gains or minimize their losses. Game theory assumes rationality. Players make decisions logically, considering their own interests. Whether it's a move in chess or a pricing decision in business, game theory seeks optimal solutions. Now let's explore how game theory specifically applies to operations research. Strategic decision making. So game theory guides strategic choices, whether it's bidding in an auction, negotiating contracts, or forming coalitions. In terms of resource allocation and optimization, allocating scarce resources efficiently, such as production capacity or research funds, is a critical application. Supply chain coordination. So coordinating suppliers, manufacturers, and distributors involves strategic decisions. Game theory ensures smooth operations. What about pricing strategies? So optimal pricing in competitive markets, considering rivals' reactions, is a key area. About bidding and auctions, game theory models help determine optimal bidding strategies also. What about queue management? So even managing queues, for example, waiting lines at service centers, can benefit from game theory. So as mentioned, game theory isn't confined to academia. It's all pervasive. From military strategy to environmental negotiations, game theory shapes real-world decisions. So whenever there is a conflict, uncertainty, or strategic thinking, game theory comes into play. Remember, whether you are a researcher, a business leader, or simply navigating life's choices, game theory offers valuable insights. Now let's break down the fundamental terms related to game theory. So who is a player? A player refers to the participants in the game, whether they are individuals, firms, or any decision makers. Players make choices based on available strategies. What is strategy? It represents the predefined rules guiding a player's actions. Each player selects a strategy to achieve their objectives, for example, pricing, advertising, or resource allocation. Optimal strategy is the strategy that maximizes the player's gains or minimizes their losses. So rational players aim to choose the best course of action given their opponent's moves. There is something called payoff in games. So the outcome resulting from playing the game is called payoff. Payoffs can be monetary, like profits, or utility, like satisfaction, or any measurable outcome. There is something called a payoff matrix, which is made of payoffs, different payoffs within the game. So it is a table showing gains or losses for each player based on their chosen strategies. Rows represent one player's strategies, columns represent the other player's strategies. What is saddle point? So at equilibrium point in the payoff matrix, a balancing point is called a saddle point. At this point, neither player has an incentive to change their strategy given the opponent's choice. What is the value of a game? So the expected outcome per play when optimal strategies are followed is the value of the game. It represents the long-term average payoff in repeated games. Remember, understanding these terms helps us navigate the strategic landscape of game theory. So now, let's consider simple games, right? So a two-person sum game is an example of a simplest game. Let's break down the concept of a two-person zero-sum game. In this game, we have two players engaged in strategic interaction. The critical feature is that one player's losses exactly balance the other player's gains. The net sum of gains and losses is always zero. Imagine it as a seesaw. When one side goes up, one player gains, the other side goes down, that is, the other player loses. Now let's explore the payoff matrix rules for such games. So let's consider players and activities. So assume we have two players denoted as A and B. Player A has an M available activities while player B has N available activities, as you can see here. The rows represent the activities available to player A, and the columns represent the activities available to player B. And each cell entry, like you can see here, Vij, represents the payment to player A when A chooses activity I and B chooses activity J. Now, what is zero-sum property? In a zero-sum game or a property, the cell entry in player B's payoff matrix is a negative counterpart of the corresponding cell entry Vij in player A's payoff matrix. You can see it here, like V11, here it's minus V11, and so on and so forth. So if player A gains a certain amount, player B incurs an equivalent loss, and vice versa. In summary, a two-person sum game embodies a balanced struggle where one player's success directly offsets the other player's setback. It's a fascinating concept with applications across various fields. So let's consider a two-person coin tossing game, which is an example of a two-person zero-sum game. So in this game, each player tosses an unbiased coin simultaneously. Each player selects either a head or a tail. If the outcomes match, that is, both get heads or both get tails, then player A wins ₹4 from player B. Otherwise, player B wins ₹3 from player A. Let's assume that. Now, this game falls under the category of a two-person zero-sum game because winning for one player implies a loss for the other. Each player has two pure strategies to choose from, heads or tails. As you can see, heads or tails, right? So player A gets ₹4 if both the outcomes are same, and player B loses ₹3. So this is the outcome matrix for this game. Okay. So games can be classified into mixed and pure strategy games. Now, what are pure strategy games? So the simplest type of game is where the best strategies for both players are pure strategies and they stick to the same strategy throughout. This is the case only if the payoff matrix contains a saddle point or the point of equilibrium. Now, to solve a pure strategy game, we use maximum and minimax criteria, which we will discuss in upcoming videos. However, for now, it suffices to say that these criteria help minimize losses and maximize profit for both players. Okay, here is something exciting. In the upcoming videos, we'll cover an example of a pure strategy game using Python program. Okay. Now, let's come to mixed strategy games. These are games without a saddle point. If a game does not have a saddle point or a balancing point, then both players must determine an optimal set of strategies to find an equilibrium point. They must struggle to do so. The optimal strategy mixture for each player may be determined by weighing each strategy by its probability of being chosen. The value of such a game represents least payoffs, which players A and B can expect to win and lose respectively. Now, what is an optimal strategy? The players need to decide which strategy to pursue on profit maximization and loss minimization. Such a strategy is called an optimal strategy. Now let's consider a classic example of a pure strategy game, the prisoner's dilemma. In this game, the two suspects are arrested for a crime and they face the following choices. The first choice is to cooperate or stay silent, wherein both prisoners remain silent, not confessing to the crime. If both cooperate, they each receive a reduced sentence, let's say 1 year in prison. If they betray, which is the second condition, they confess, and one prisoner confesses, implicating the other. If one betrays while the other cooperates, the betrayer gets an even lighter sentence, let's say 6 months, while the other faces a harsher sentence, let's say 5 years. So the dilemma arises because each prisoner wants to minimize their own sentence. However, if both betray each other, they both end up worse off than if they had both cooperated. Now, the payoff matrix for the prisoner's dilemma looks like this. You can see the payoff matrix right here. Here, the first number in each cell represents the payoff to prisoner A. The second number represents the payoff to prisoner B. Now, despite both players having an incentive to cooperate, which would lead to the best overall outcome, the dominant strategy for each prisoner is to betray the other. As a result, they both end up with suboptimal sentences. This scenario illustrates the tension between individual rationality and collective welfare, making the prisoner's dilemma a fascinating example of a pure strategy game. Let's consider another example. This is one for mixed strategy. Now, a mixed strategy is one where a player plays some of the available pure strategies with certain probabilities. It's best understood in repeated games where each player's aim is to keep the other guessing. An example of a mixed strategy game is the rock, scissors, papers game, which you're all aware, almost all of us have played it in our childhood. In this classic game, each player chooses rock, scissors, or paper. A mixed strategy involves playing each option with equal probability, that is 1/3 for each option. By mixing their choices, players keep their opponents uncertain about their next move. So let's construct the payoff matrix for the classic game of rock, paper, scissors. In this game, two players, A and B, each choose one of the three strategies: rock, paper, or scissors. These are three strategies. The outcome depends on the combination of their choices. If both players choose the same strategy, it's a tie, which means a payoff of 0. Otherwise, rock beats scissors, that is, rock is greater than scissors, or scissors beat paper, scissors is greater than paper, or paper beats rock, paper is greater than rock. So here's the payoff matrix. As you can see here, in the matrix, the rows represent player A's possible strategies, that is RA, PA, and SA. Okay. And the columns represent player B's possible strategies, that is RB, PB, and SB. The numbers represent the payoffs for player A: positive for a win, negative for a loss, and 0 for a tie. So interestingly, rock, paper, scissors is a zero-sum game, meaning there is no win-win situation, only win-lose or a tie. Okay, let's delve a little bit into the tools for solving games within the context of game theory. There's something called Nash equilibrium. It's a very important concept, and it's named after mathematician John Nash. It's a critical concept of game theory. It represents a stable outcome where no player has an incentive to deviate from the chosen strategy, given the opponent's strategies. In other words, everyone plays their best hand considering what others are doing. So Nash equilibrium is like the delicate balance point in a seesaw where neither side wants to shift. In the rock, paper, scissors game, in the previous slide, the Nash equilibrium occurs when both players play each strategy with equal probability, that is 1/3, resulting in an expected payoff of 0 for both players. However, in practice, human players often deviate from true randomness due to cognitive biases and patterns. So what are dominant strategies? Dominated strategies, you can imagine you're playing a game and one of your options consistently leads to worse outcomes, regardless of your opponent's moves. Our dominated strategy is precisely that, an inferior choice that you should eliminate. Rational players discard dominated strategies to focus on better alternatives. What are dominant strategies, on the other hand? So now let's flip the coin. What if you have a strategy that's always optimal regardless of what your opponent does? That's a dominant strategy, the one you'd play every time, no matter what. Dominant strategies simplify decision making because you don't need to worry about your opponent's moves. In summary, these tools help us navigate the strategic landscape of games, whether it's finding equilibrium points, eliminating weak choices, or identifying dominant moves. Game theory equips us with powerful insights. So folks, that's it for now. See you in the next video. Thanks for watching till the end.